Hello everyone, this is our first video on Analytic Inverse Kinematics. If you remember in forward kinematics problem, I give you the joint variables as well as the geometry of the robot, and then I ask you to find for me the rotation matrix and the position vector of end effector in base or inertial frame. Right, which you could do it with DH convention or the vector addition method or any other method. Now in inverse, it's backwards. Clearly, I will give you the rotation matrix and the position of end effector in base plus geometry of the robot, and then I ask you to give me back the joint variables, which basically means solving for a set of algebraic equations that are nonlinear, and these equations are all coupled, so you have to solve them at the same time. Let's just consider the example of the Stanford robot, right? Which, as you can see, it has 6 degrees of freedom. And if I give you this homogeneous transformation matrix of E in I as this 4x4 matrix, where this 3x3 minor of it is the rotation matrix, and then this 3x1 vector here is the position of the end effector in base. Since these 12 components, right, in the H, in general, are functions of the joint variables from 1 to 6, then these are the 12 equations that you will get, right? So each set of these formulas that you see is one of those numbers, right, that you set equal to that variable based on every joint variable. Not all of them are the function of all 6 joint variables, some of them are. But in general, you clearly get 12 equations. These last 4 numbers, as you know, they're always 0, 0, 0, 1. So I have 12 equations, and the matter of fact is I only need to find what? 6 unknowns, theta 1, theta 2, theta 4, 5, and 6, and D3, which is the value of this prismatic joint. So first of all, I have 12 equations. Second of all, and 6 unknowns. And that means my system of equations is what? Is over constrained, right? So my system is over constrained. And you might say, well, is there then an accurate solution? Because typically when your system is over constrained, that means you can at best find what? At least a square solution or something, an approximate solution. But the matter of fact is, in this case, there are what? There are 6 constraints here. What are those constraints? Well, those are the constraints for the rotation matrix. If you remember, each column of the rotation matrix has a magnitude of 1, and then each column is perpendicular to the rest of the columns. So column 1 dot product with column 2, column 1 dot product with column 3, column 2 dot product with column 3, they're all 0, and magnitude of column 1 is the same as magnitude column 2 is the same as magnitude column 3 equals 1. So those are those 6 constraints coming from this rotation matrix. So what you need to solve for are 12 equations and 6 unknowns, but there are 6 constraints which are in terms of all of these variables, and that makes the solution of that almost impossible if you don't have a spherical wrist here, which in this case you do. But if you don't have a spherical wrist and the robot has 6 degrees of freedom or sometimes more, then in general, the analytic solution of inverse kinematics problem is not always possible. For some scenarios, it is possible. For some scenarios, it is not. And even when it is possible, it's not really a trivial thing. So that's one problem. The other problem we have is the multitude of solutions. If you remember, if I give you the variables theta 1, theta 2, theta 4, 5, 6, and D3, and the geometry of the robots, then there is what? One unique solution that you will find for the rotation matrix and the position vector. As long as the values I give you for the 6 variables are within their mechanical limits, then there is always what? A unique solution to the forward kinematics problem. On the other hand, if I give you the inverse problem, and I ask for joint variables, we can see there are different scenarios. There are scenarios where there is no solution at all for Q's. There are scenarios that there is a unique solution. There are scenarios that there are several solutions. And there are scenarios that there are infinitely many solutions, okay? So that's another big important difference between forward and inverse kinematics. Inverse kinematics can have no solution, unique solution, several solutions, or infinitely many solutions, while again forward has only a unique solution as long as the joint variables are within the mechanical limits. And I'll show you all of these scenarios here through even simple examples. So in general, if you want to put it in a nutshell, inverse kinematics problem is much more difficult than forward kinematics. Okay. So to start explaining all of this, we start with the kind of the simplest robot that we know, the 2 degree of freedom planar arm, right? So you have 2 members here with sizes of A1 and A2, and let's say here we attach an end effector here, a gripper, let's say. And the positions of the end effector in base, x of e in 0 and y of e in 0, these 2 guys are given to me. As well as what? A1 and A2. And then the goal is to find the angles of the 2 members, theta 1 and theta 2, correct? So that is your analytic inverse kinematics. So let's see how we can potentially find solutions here. So if we write our forward equations, forward kinematics equations, then you know that x of end effector in base is equal to A1 times C1 plus A2 times C12. As you remember, C1 is cosine of 1, theta 1, C12 is cosine of theta 1 plus theta 2. And similarly, y of end effector in base is A1 S1 plus A2 S12. Okay, so clearly you have 2 equations and 2 unknowns. The equations are nonlinear in terms of the unknowns. But in this case, because the robot is not very complicated, we can find solutions both using geometrical approach and also direct mathematical approach, pure mathematical without any geometrical interpretation. First, geometric approach. So in geometric approach, here I'm going to name origin O. I'm going to name this first joint A, or second joint really, and the end effector E. I'm also going to call this point where where this x of e is happening, this point, if you don't mind, I would call that point C. And I also need to draw a perpendicular from E to the line of action for member 1. So from here, I draw a perpendicular line, this line here, and the bottom point of this, I call it D. So I have O, A, E, C, and D. Good. First question is, if I want to find this angle here, this one, I can call it whatever you want. Maybe I call it angle beta. So how do I find angle beta? Well, angle beta is in the triangle OEA. And this triangle, 2 sides of it are A1 and A2, and this side, which I called C, the hypotenuse, is clearly what? It is the square root of x of end effector squared plus what? y of end effector squared, right? It's the hypotenuse of the triangle OEC. So clearly I can let me write it bigger a little bit. So this guy here is the square root of x of end effector in base squared plus y of the end effector in base squared. Right? So you have this triangle. This is A1, this is A2, this angle is beta, and this side is that C. How can I find C? Using the laws of cosine or law of cosine. Law of cosine says what? It says C squared equals A1 squared plus A2 squared minus 2A1 A2 cosine of beta. And you know that C squared, based on what we had, is going to be that whole thing where the square root is taken out. So it is going to be x of end effector in base squared plus y of the end effector in base squared. Correct? So from here, I can clearly find what? I can find cosine of beta. But you know beta is related to theta 2. Clearly beta plus theta 2 is what? 180 degrees, right? So beta plus theta 2 is pi. So when two angles are such that sum of them is 180, you know that cosine of one is negative of cosine of the other. So instead of cosine beta, I can use negative cosine theta 2, correct? This we know from trigonometry. So if I plug it up here, then it is going to be, as I said, negative cosine of theta 2. And then these two negatives would cancel out. And so from here, I can directly find cosine of theta 2, which is going to be x of the end effector in base squared plus y of the end effector in base squared minus a1 squared minus a2 squared, then divided by 2a1 a2. Okay, and this formula can give me cosine of theta 2, and now you might say, well, I take a cosine inverse from both sides, and that gives me theta 2, one of the two unknowns. Yes, you can do that, but the problem with the arc cosine function or the regular arctangent function is they are not quadrant corrected. Okay, so what we do typically in robotics, instead of using the regular arctangent, which only takes the ratio of y over x or arc cosine, we use this quadrant corrected function, which we call arctangent 2, which you know there is this function in MATLAB, arctangent 2, which it takes both y and x instead of the regular arctangent that takes what? Y over x. So for a regular arctangent function, the ratio matters. So if both of them are positive 1 or negative 1, the ratio is going to be 1. While for this one, positive 1 means it is in the first quadrant. Negative 1 means it is in the third quadrant. Okay, so this arctangent is not only more accurate than the regular arctangent, it is more accurate than arc cosine. Okay, which is basically x over r. Because again, for this one, as long as x is positive, it does not care, right? Whether it is in what? First quadrant or the fourth quadrant. For both of them, x is positive, or if it's negative, again, it could be in the second quadrant or the third quadrant. It only cares about sign of x because this square root is always positive. So instead of regular, as I said, arc functions, we use arctangent 2. How? Well, from here, if I call this whole ratio, which is just a single number, right? Because x and y are numbers, a1 and a2 are numbers. If I call this whole ratio just number d, and that d is equal to cosine of theta, then from here, sine of theta 2 is going to be plus or minus square root of 1 minus d squared, or 1 minus cosine squared. So now I have both sine of theta 2 and I also have what? Cosine of theta 2, which corresponds to what? Y and x. Therefore, I use what? I use these two things I found for sine and cosine, and then I find theta 2 through arctangent. So theta 2 is going to be arctangent 2 of what? Plus and minus square root 1 minus d squared, which is sine of theta 2, and then the d itself, which is cosine of theta 2, where d is this ratio here. Okay, so that is ratio, and this is what? D. So this is the formula I use to calculate what? Theta 2. And clearly this formula tells you that there are two answers for theta 2. One is for positive square root, the other one is for negative square roots. And I'll show you when we are done with the solution. I'll go back and show you what's the meaning of positive and negative. Okay? But clearly you see that your inverse solution can have more than one answer. It can have two answers as far as just theta 2 so far. So good, I got my theta 2. Now what? Now you might say, well, plug that theta 2 back here in one of these and find theta 1. Yes, but that I can do with a mathematical approach. As I said, I want to find theta 1 and 2 with geometry. So then you might say, well, how do you find it with geometry? This is what I do. So here I would call this angle, this big angle here, this one. This angle, you can give it again any name. Maybe this angle, I call it gamma, if you don't mind. Right? So that angle is gamma. And I also have this smaller angle, this one. And this angle, again, I can call it something else. Let's say, for example, here, maybe delta. So gamma minus delta is clearly what? Theta 1. So theta 1 is gamma minus what? Delta, right? So if I want to write it somewhere, then clearly your theta 1 is gamma minus delta. What is gamma? Well, gamma is in the big triangle OEC. The y of it is y of the end effector, the x of it is x of the end effector. So I can use that same arctangent 2 function I just told you and pass to it y of the end effector and x of the end effector. And that will give me back gamma minus. What is delta? For delta, I use this triangle OED. If I draw that OED for you here, it has this part of it A1, this part of it is A2, and this part of it is theta 2. The adjacent part of it is going to be A1 plus this much. Right? Because this is A1 from here to here, plus that is A2, that is theta 2, that is A2 cosine theta 2. And this in opposite to it is A2 sine theta 2. So clearly the whole adjacent is A1 plus A2 cosine theta 2, and the one opposite to it is A2 sine theta 2. So if I pass those two arguments to the arctangent 2 function, right? So A2 sine theta 2 and A1 plus A2 cosine theta 2. That should definitely give me that angle delta. And that's what you see here. And guess what? I already calculated theta 2 in the previous step. So I just need to plug it into this sine and cosine, and this one gives me what? Theta 1. Again, this theta 2, the sine and the cosine of it should be used here. Done. And these are my solutions, theta 1 and theta 2. So for each theta 2, there will be a corresponding theta 1, of course. So in general, there are two solutions, one for the positive square root, one for the negative square root, okay? And so the inverse kinematics problem in general can have two solutions. Now, what are those two solutions look like? Let me show you that. So if this is the base frame and this is a specific position and I want to reach that point, one way to reach it is this. The other way to reach it is this. So of course the end effector orientation will be different, but here we don't care about the end effector orientation, we only care about the end effector position. So in one of them it will be like this, in the other one it will be like that. Because it's rigidly attached to member 2, but we just need to reach that point, correct? So in this case, clearly your theta 2 is positive, because it is counterclockwise. And in this case here, clearly your theta 2 is what? Negative. Okay, so this condition that theta 2 is positive, we call it what? We call it elbow down. And this one, we call it elbow up. So there are two separate solutions for the problem of inverse kinematics, elbow up and elbow down. Now, you might say, well, is there any scenario where there is no solution or one solution? Sure. When is that? Well, if this point that I'm going to reach is outside the workspace, then there will be no solution. But you might say, okay, where is the workspace, or how large is the workspace? Well, here, if we assume for the moment that A1 is bigger than A2, so this A1 that we have is what? Bigger than A2, then what? Then what you will have is the maximum reach that you can have is when theta 2 is 0, so the two members are aligned. Then the maximum radial distance you can reach is A1 plus A2, and the minimum that you can reach is when member 2 is completely again aligned back on member 1, but theta 2 is pi, so it is backwards here. In that case, your workspace is going to be basically a disk. Okay, so you will have a disk here, and you will have another disk here, both centered at origin, where the radius for the big guy is A1 plus A2. Let me show you the outside. And the radius for the smaller one is A1 minus A2. So this area here that I'm using the hatching lines, this is going to be your workspace. Okay, assuming that A1 is bigger than A2. You might say, what if A1 is equal to A2? When then there is no disk. It's going to be a solid circle. You can reach the origin as well. And if A2 is bigger than A1, then what? Then again, the same problem, because now if it's completely, member 2 is moved back and theta 2 becomes pi, then you will have something like this. So this is A1, this is A2. Again, can I reach origin? No, I cannot. So again, you will have the same thing, but this radius is going to be A2 minus A1. So as long as A1 and A2 are not the same, you will have a disk. When they are the same, then the disk will be, there will be no hole in the middle of the disk. It's going to be a solid circle. So that's my workspace. And as I said, if the point you want to reach is outside this workspace, then there is what? No solution, right? And what if it is on the boundary of the workspace? So what if the point I want to reach is exactly on the boundary? Then, of course, here you have to make the two members completely stretched out. So theta 2 has to be 0. And then theta 1 is just given by arctangent 2 of y of end effector and x of end effector. Okay? And the same thing here. Right? That's the same thing. Theta 2 is pi, and again, theta 1 is given by arctangent 2 of y of the end effector and x of the end effector. So I'll write it down for you, but just pay attention. On the boundary, there is a unique solution. Outside the boundary, there is no solution. Inside the boundary, there is elbow up and elbow down. And you might say, is there any case of infinitely many solutions? Yes, there is. And that is only when A1 is equal to A2. So if A1 is equal to A2 and the point that you want to reach is origin. Okay, so let me show you that. If A1 is what? Equal to A2 and the point you want to reach is origin, then what's going to happen? So here is one of your axes. This is the other axis. And here I have the workspace, which, as I said, it is a circle centered at origin. A1 is equal to A2, and you want to reach origin. Well, one member is going to be this way, the other member is going to be like that. So I can reach it this way. Or one member can be like this, the other member can be like that. Or it can be like this and then back like that. So in this scenario, theta 2 is pi and theta 1 is what? Arbitrary. Let me write it down for you. So theta 2 is pi, but theta 1 is arbitrary. And arbitrary means what? It means infinitely many solutions. So the only case is this, reaching origin when the two members are equal size, then there are infinitely many what? Solutions. Okay, so this is the overall analysis of inverse kinematics for 2D OF planar arm. Now, can I find the conditions mathematically for when, right? Let's say I want to write a code for when there is no solution or there is what? There is a unique solution or there are two solutions. How can I find that mathematically? Well, it all goes back to this definition of D. Remember, D is cosine of theta, and cosine of any angle is between -1 to 1, correct? So that gives you the condition that you need. So let me write it down for you here. So remember, cosine of theta 2, which is equal to this ratio, it is going to be between -1 and +1, right? That's all you can do. Therefore, it gives you limitations on where you want to put your position of the end effector. Now, if you use the right-hand side part of it and you cross multiply, you will get x of the end effector in base squared plus y of the end effector in base squared minus a1 squared minus a2 squared less than or equal to a1, a2. Then you'll take these two negative terms and take them to the right-hand side. So what you will get is this whole thing here is going to be what? Less than or equal a1 plus a2, the whole thing squared, right? Because that's what it gets, a1 squared plus a2 squared plus 2a1, a2. On the other hand, if you do this portion of it, and you do it, what will you get? You will get that whole thing again is bigger than or equal negative 2a1, a2, right? So you will get something like this. If I do it, let me bring it down here. So if you do that portion of it, then you will get bigger than or equal negative 2 times that. And again, if you take these two terms, negative, take them to the other side, then you will get what? You will get your xe squared plus ye squared is bigger than or equal a1 minus a2 squared. And so from these two, you will get your condition that what? The radial distance, if you take the square root, the radial distance to the end effector, which is this square root, has to be between the two values. One of them is a1 minus a2, or you can say absolute value of a1 minus a2, and the other one is a1 plus a2. So this is what? This is the condition for having a solution. Now, if the equality holds, either this one or that one, means you are on the boundary, so there is one solution. If the inequality holds, then what? You have two solutions. If it's outside the range, then there is what? No solution, correct? So this is the general condition for having any solution. But again, equality means one solution, you are on the boundary. Inequality means two solutions, elbow up, elbow down. And if it's outside this range, means there is what? No solution, okay? And the exceptional case is when a1 is equal to a2 and you want to reach origin. Because then this thing is going to be 0. This left-hand side is going to be 0, and that guy is going to be 2a. And since 0 is always bigger than or equal 0, then it means theta 1 can be arbitrary. So this is how you handle the problem of what? Inverse kinematics for 2DOF planar arm with all cases. Now, is there any other way to solve this? Yes, the way to do it is the mathematical way without any geometric help or interpretation. So since I want you to work with trigs and be good at it, I'll show you the second way that here we solve this problem without any geometric approach, because I think it is important. So what we do here in this case, we raise each equation to the power 2. So these are the equations of the forward kinematics. I raise each one to the power 2 and then I add them together. If I do that, I will get this guy here. On that side, it's two terms. It's a binomial. When you square it, you will get a1 squared c1 squared plus a2 squared c12 squared plus 2a1 a2 c1 c12. That's for this guy here, and then plus a1 squared s1 squared a2 squared s12 squared, and then plus 2a1 a2 s1 s12. And now when you add them, some of these two terms, since they have the common term a1 squared, is going to be s1 plus c1 squared, which is 1, right? So summation of these two will just give me a1 squared. Summation of these two terms, because again that's c12 and s12 squared, and they both share a2 squared, so summation of these two will give me a2 squared. And then these two terms, if you look at them, they have the term a1, a2, which I can factor out. So if I do so, I will get xe squared plus ye squared equals, as I said, this is going to be a 1 squared, this guy is going to be a 2 squared. Those two that have 2a1, a2, I factor it out. And so the result is going to be cosine 1, cosine 1, 2 plus sine 1, sine 1, 2. And now you might say, well, what is this guy? And that is where tricks come to help you. Cosine of a plus b, as you know, or a minus b in this case. Cosine of a minus b is cosine a cosine b minus sine a sine b. And that's what you have, or plus, sorry. That's what you have. Product of two cosines plus product of the sines. So here, what I will do, I will consider my a to be 1, 2, and I consider my b to be 1. Then a minus b is going to be 1, 2 minus 1, and 1, 2, remember, that's theta 1 plus 2, this is theta 1. So the whole thing is simply going to be what? Theta 2. So this whole thing is what? Cosine of theta 2, and guess what? If you look at this equation, xe squared plus ye squared is a1 squared plus a2 squared plus 2a1, a2 cosine theta 2. This is the exact same thing that we got here when we use the geometric approach. So if I define again the same d ratio that I had, and then the plus minus square root 1 minus d2 squared, that should give me the exact formula for what? Theta 2. So this one will lead to the exact same formula that I had. No difference. Did I use any geometry? No, I did not. Correct? Now you might say, well, can you get theta 1 to be the same formula that you derive using geometry without any geometrical approach? Can you continue this solution and get the same theta 1 that you got last time? Yes, I can. How? Well, let's go ahead and see how we can potentially find what? Theta 1. So now what do I do? Now, since theta 2 here is a known value at this point, I found it, then instead of adding these two and the square of them, here I do something else. So let me show you what I do next. This time I'm going to expand them. So if I do that, this is going to be a1 c1, so plus a2, and c1 2 means c1 c2 minus s1 s2. But 2 is known. When 2 is known means the c2 and s2 are known values, so I treat them as constants right now. If that's the case, then only I have a c1 term here and another c1 term here. So if I factor out the c1 term, it is going to be c1 times what? Here is a1, that is going to be plus a2 c2. And then this term, if I factor out s1, is going to be negative a2 s2. Okay, that is x of e. Similarly for y of e, it is going to be a1 s1 plus a2. Now again, s1 2 is s1 c2 plus c1 s2. And again, c2 and s2, I treat them as constants. If you factor out, this time the c1 term, the coefficient of that is going to be what? It's going to be a2 s2. And the s1 term, if you look at it, the coefficient of it is a1. And then plus what? a2 c2. Good. So that is going to be a 2x2 set of equations where the unknowns are C1 and S1, and the coefficients are these guys, which are just constant at the moment, and the right-hand sides are XE and YE. So you can write it in vector format or matrix format as XE and YE are a coefficient matrix times what? C1 and S1. And this coefficient matrix is A1 plus A2 C2, negative A2 S2, positive A2 S2, and again A1 plus A2 C2. If you do that, then if you call this matrix A, then and call this side B, then C1 and S1 are clearly A inverse times B, right? And to do that, we need to, for inverse of a 2x2, we swap the diagonal elements. In this case, they are the same thing, so it's not going to affect anything. And then the anti-diagonal, we negate them wherever they are. So that makes it like this. And then we divide it by the determinant of the matrix, which in this case is the product of the diagonals minus the product of the anti-diagonal. They are the same term. There is another minus here, so it's going to be make it plus, and then it's going to be A2 squared is 2 squared. This one is that A1 plus A2 C2 squared. Okay, if we continue here, when you expand this, it's going to be A2 squared C2 squared. Summation of that with this one is just going to make it A2 squared. That's A1 squared. And then you will get 2A2 2A1 A2 C2. And here you will get the first term is going to be A1 plus A2 C2 XE, then plus A2 S2 YE. This is the first element, and the second element is going to be negative A2 S2 XE, then plus A1 plus A2 C2 YE. Okay, so this is going to be C1 and S1. And since they both have the same denominator when you use the arctangent function, so theta 1, which is arctangent 2 of S1 and C1, if they both have the same denominator, and that denominator is this number here, if I neglect that because they have the same ratio, then I can just look at what? These guys that they have, right? So it is simply can be written as arctangent 2 of basically these guys here that I just showed you. A1 plus A2 C2 XE, right? Or that's actually the sine term. So negative A2 S2X and plus A1 plus A2 C2 Y. That is the Y term, and then I have the X term, right? Or if I just want to show you that this one gives you the same formula as what we got here, all you need to do is to use the arctangent A minus arctangent B, and from trigonometry, if you remember, arctangent A minus arctangent B in general is what? It is arctangent of what? It's going to be A minus B divided by 1 plus AB. Okay, so if I apply that to this formula here, right? Because this is like your A and this is like your B. Then your theta 1 is going to be what? Arctangent of, as I said, A minus B, which is what? In this case, A is going to be the ratio of y over x. And then B is going to be the ratio of sine over cosine. And then 1 plus the product of these terms. And clearly here, if you take a common denominator, right, they both have the common denominator of xe times a1 plus a2 c2, then you will get what? You will get a1 plus a2 c2 times y of e minus a2s2 x of e, then divided by a1 plus a2 c2x of e plus a2s2 y of e. Okay, so this is going to be your theta 1, this ratio. And if you look, that's the exact same thing that you have here. Because all you need is to just divide here. Instead of use arctangent 2, use the arctangent. And if you do that, you will get the exact same thing as what you got in the other one, correct? Because this one is sine, that one is cosine. So this bottom one is sine, the top one is cosine. They both have the same denominator, so when you divide, that denominator is going to go away, and you clearly see that you will get the exact same thing here. Let me just write it for you. Right? So here gives me the exact formula as the other one. So I could solve it both geometrically and by pure math. I could look at all different possibilities of inverse kinematics. And in the next video, I'm going to go over more complicated robots, Ascara, 6DOF, and so on. And I'll show you possibilities of solutions for those. I show you under which condition you can guarantee an analytic solution, and talk about decoupling, inverse orientation, and so on. So hopefully this video was useful to you, and I will see you in my next video. Thank you.